Hello and welcome back. Today is the second day of the second week of this course. So, in the previous class, we learned about population inversion, and we learned that in order to have a laser action, we need to have population inversion. That is, the population of the excited state should be higher than the ground state. And when I say excited state and ground state, it means that these two states are involved in laser action. That means that they are connected by a downward or coupled by downward transition. And we also learned that it is not possible to have population inversion in a two-level system, and two-level system is the one that we started with. Okay, we did all our formalism using two-level system. So, toward the end we posed a question that two-level system cannot work as a laser, as it cannot have population inversion. Can a three-level system give rise to population inversion, and hence can it work as a laser? So, we started finding out about that one. So, we will start from that point only. So, we will have a three-level system. So, for simplicity, I am marking them as 1, 2, and 3. Okay. So, I marked them in this way just to have simplicity. So, 1 and 2, if I forget about the existence of 3, is just like a two-level system. So, I know in that case I will not have any population inversion, hence no laser action. Now, what happens in a three-level system? So, first we have to think about what are the transition probabilities here. So, I have total 3 states. So, there are total 3 pairs of system between which transition can take place. So, I can have a transition from 1 to 2. I can have transition between 2 and 3. I can have transition between 1 and 3. Okay. So, these 3 types of transitions are possible. Now, let us see what are the conditions under which these 3-level system can work as a laser. So, the answer of this question is yes, 3-level system can work as a laser. Okay. So, now under what conditions? So, first is the transition that I will consider from 1 to 2, as we have done already. Okay. So, we have to bring in a photon to make the atoms in this state 1 to have a transition up here. All right. Now, if it just comes back here, I know it is not possible to have a lasing action. But if I have the properties of the states 2 and 3 such that level 2 transfers its population to level 3 non-radiatively. So, in other words, if I say that if state 2 decays non-radiatively to state 3, and if that decay happens very fast, okay. So, we show the non-radiative transitions by this wavy arrow. Whenever I show transitions involving states, not this part, okay, the transition involving these states, the solid straight line arrow means a transition in a radiative manner. On the other hand, the wavy arrows signify non-radiative transition. So, if this the population in this state after this absorption brings back the system to level 3, and if that process is very fast, what does that mean? If I say this one state 2 has a lifetime of tau 2 and the lifetime of state 3 as tau 3, then if tau 2 is much shorter than tau 3, what does this mean? It means state 3 is very short lived, whereas state 3 is long lived. Okay. So, under that condition it will non-radiatively decay. Okay. I am assuming that it decays down here non-radiatively, no radiative decay I am considering. Okay. Radiative decay will complicate the process. Now, this non-radiative decay will put atoms here, right. Now, this first process, that is this absorption. So, we are providing an external stimulus in form of photons to take this system from here to here, and this is known as pumping. And this photons that we use is called pump. So, I am providing a pump to take the system from 1 to 2, and then non-radiatively this population is being transferred here. Now, tau 3 is fairly large. Okay. So, tau 3 will not decay down here very fast. Okay. Now, another thing to consider here, that this level 3 and level 1 must be radiatively coupled, okay, and a downward transition should be possible. Then only I can think about a laser action. If this state also non-radiatively decays down to this state, then I do not have any emission, right. Emission means it will have a radiative process involved, right. So, the decay of a state from excited to ground state, this decay should emit photon, then we have a radiative process, and here it should decay down to this state radiatively. All right. Now, if I consider a spontaneous emission, then it will have its own time, it will take its own time to come down here, okay, and that can be few nanoseconds, that is 10 power minus 9 seconds. Now, if this, say let us say we give certain numbers. So, this process, suppose it is 10 power minus 12 second or a picosecond. So, right after transfer of the population to this state 3, state 2, within a picosecond it comes over here. Now, I am continuously pumping this system, right. So, every time I pump it goes and very fast it comes down here, right. So, slowly what is happening, the population of this state, state 1 is reducing, correct. So, this population reduces, and here we have barely any population developing, because as soon as it goes here it comes down here by non-radiative decay. So, over the period of time the population of this state grows while the population of this state shrinks. So, ultimately I will have a situation where the number of atoms here will be larger than the population here. This is just to show you. Okay. So, at that condition I have already achieved here, if I denote the populations by N2, N3 and N1 respectively, then N3 becomes greater than N1 at some point of time, right. At a 0 time this state has pretty much this total population, and as soon as we start pumping it grows here. So, after a certain time I will see that N3 is greater than N1. And now here this N3 and N1 is pretty much like what we had in our previous class as N2 N1. So there I needed to have a a condition that is N2 greater than N1. Okay, here also I have this same system where N3 is greater than N1. All right. So although we are not having a population inversion between the initial two states, that is 1 and 2, but a third state which has a larger lifetime, and we call this as a metastable state, as we have mentioned. Okay, it is metastable. It is not stable forever, but its lifetime is much more than this state. So we ultimately achieve so called population inversion, and therefore this system can work as a laser. So Threelevel system can have population inversion right. So that means it can work as laser. Okay. So now how it will work as a laser. Okay. So let's talk about little bit practical parts. So when I am pumping, I am giving the energy that is equal to this E2 minus E1, right, and the lasing action that is happening here, that is, let me use a different color. So like this, right. So this is my stimulated emission, and this will give me my laser action if I can have amplification, right. So I can see that stimulated emission we can have, right. My aim is to amplify this stimulated emission. So in order to amplify the stimulated emission, that means we have to overcome the spontaneous emission, we have to overcome the absorption, then only I can have a net gain. So we will have an amplification of stimulated emission, and it is in optical frequency, and we call it laser. Now as I said earlier that I am using a photon, say, that is having energy h nu 1 2, and this light has energy h nu 1 3. Let us put it in that way. So it is equal to the gap between 3 and 1. So how do we start the stimulated emission? Because stimulated emission requires a stimulus, so it will not happen by its own, correct. So how this stimulation take place? If you think about, this state is coupled to this state by a downward transition. That means from here a downward transition can happen radiatively. So at some point of time there will be a spontaneous emission. So one atom in state 3 can just drop to state 1 by spontaneous emission without need of any external stimulant. Now that photon exists in the system, and that photon can interact one of these excited atoms and bring it down, giving total 2 photons. Then those 2 photons can interact with another 2 excited atom and bring down total 4, give 4 photons, and in that way it can keep going and going and going. So in this system, spontaneous emission triggers stimulated emission. Stimulated emission, right? This must be clear by now. I do not need to put any light from outside to stimulate this process. These photon which is coming due to spontaneous emission can trigger the stimulated emission. And what will happen in that case? In this Threelevel laser system, I know that okay, it will take some time to build up the population here, and it will certainly take certain amount of time to create the inverted population or to create the population inversion. So, once the population inversion is created, we will have on spontaneous emission taking place, and that will trigger the stimulated emission, and it is highly possible that then it will create like an avalanche. So, one photon comes down, that goes hits here, 2 photons goes out, those 2 hits this 2 giving 4 and so on. So, altogether all the excited atoms at state in the state 3 can just collapse to the ground state. So, what does that mean? That I will get a bunch of photon within a very short period of time, and then this whole state is empty because all of them have gone down within a very short period of time, correct? So, I get large output. Now, at that condition what happens? All the molecules are back to the ground state, and the ground state population is way much higher than this state at that point of time. Again it will take its own time to build the population inversion, and again some spontaneous emission will trigger the stimulated emission. So, the take home message is that from this Threelevel system I will get short bursts of photons. Okay? So, this is time, okay, and this is my amplitude. So, I guess this point is very clear here, right? By the design, it works in such a way that it cannot give continuous flow of photons or continuous output of photon, but it gives as a burst of photon which is known as pulse. So, these are pulses. So, this is one pulse, this is one pulse, this is another pulse, and this is the delay between 2 pulses, right. So, this is delay between pulses. Okay. So, we get a pulsed output from Threelevel system. So, this is first take home message that Threelevel system gives pulsed laser output. Okay. So, this is what Theodor Neumann got in 1961. Okay. So, why this is happening? Because the actual ground state of the molecule is involved in this laser process. So, this ground state is the lower state between the 2 states which are involved in lasing action. Okay. So, what happens here, it is difficult to maintain the population inversion. So, the second thing is that it is difficult to maintain population inversion in a three-level system. And because of this, actually I have an inherently pulsed laser output. Okay? So, if I cannot maintain my population inversion, then again I have to create the population inversion, and the time between the first laser output and then again the population inversion creation is essentially this time. And of course, one spontaneous photon, emitted photon, has to come and trigger the second burst. All right. So, this was the first laser that humankind invented, essentially Theodor Neumann, and this was one of the drawbacks. Okay, that it cannot be operated in a continuous fashion. Also, there were certain other things, that it has had to be pumped really hard. Okay, so that what does mean, that you have to put a lot of energy and then pump it there, so that the population created here is more than here. Okay, so this is kind of a drawback. Now, when we go from a 3-level laser to a 4-level laser, can we overcome this drawback which is given in this point 2? That is the problem of, or difficulty of, maintaining the population inversion. So, let us see if we can create population inversion in a 4-level system, and also if we can, then can it get rid of the problem that 3-level system faces. So, let us take a 4-level system in a very similar manner. So, again I will name it in the same way. So, first level is 1 and the topmost level is 2, and then I have 3 and level 4. So, we will follow the same convention. We will come with a photon and take the atoms which are here to this level. Okay. So, when I send the pump in, so this is very necessary to get familiar with these terms, pump. Okay. So, let us pump this to level 2. So, I create some population. Now, if this level 2 is just like level 2 here in this system, that is, if this level has lifetime tau 2 and this has tau 3 and say tau 4, then if tau 2 is much shorter than tau 3 and tau 3 is much greater than tau 4, then what happens? Now, one more thing also I must tell, that this state 2 can non-radiatively decay very fast to state 3, and also this state 4 non-radiatively decays to the ground state very fast. So, this process and this process are extremely fast and non-radiative. Okay? So, this is non-radiative decay and very fast, and the same is true for this one also. In that case, what will happen? After I pump here, immediately it will bring the population over here, correct? And this will take its own time, because the lifetime of this state is much higher than this one. So, it will keep building up here. Okay? So, now look at this condition, look at this particular system. Level 3 and level 4. So, level 4 has 0 population, okay, according to my drawing. I have pumped it here and it has transferred the population over here, and they are waiting there. So, there is a waiting period, they are waiting there. There is no population here. So, at the very beginning when I start pumping, I have actually created a population inversion between state 3 and state 4, right. So, N3 is higher than N4, and it is pretty much all the time. As soon as I start pumping, it creates this condition. So, it is very easy to create population inversion in 4-level system. Correct? For a moment, just come back to this picture where this level and this level were coupled by downward transition, and they are involved in lasing. So, population inversion had to be established here with respect to the ground state. So, if you have to do that, you had to really pump it hard. We told that, right. So, we have to put in lot of energy, lot of photons inside to actually create a condition where this state has more population than the ground state, which is highly, which is not the case here. Okay. So, this is a contrasting case. So, here creation of population inversion is rather difficult. Here creation of population inversion is very easy. And also we need to put little energy, much lower energy than this case. All right. So, now after saying all these things, if I also add that state 3 and state 4 are radiatively coupled by a downward transition, meaning that it can emit from here to here. So, that means these atoms excited here, they can come down to state 4 by emitting a photon. Then just imagine again, if there is a spontaneous emission. So, one photon due to this spontaneous, suppose this is making this transition. So, this is giving rise to a spontaneous emission of one photon, which triggers the decay of all these photons into this state. All right. Now, it will give a intense light as output. Now, see the contrast between this and this. Here it is continuously pumping in here, and whenever there are photons here, this is almost empty, because I have already said that this state decays to this ground state non-radiatively, and that is very fast. Okay. If you just look at this time scale, that is 10 to the minus 12 second compared to a lifetime of say much longer than that, okay, nanosecond and beyond. So, it will have ample of time to have a population inversion. So, it is therefore always having a situation where it is having population inversion. So, that means it will give, so a 4 level system will intrinsically give a continuous output of laser light, which we say continuous wave laser output. Because it maintains the population inversion. Okay. It is not difficult for the 4 level system to maintain or sustain the population inversion. So, I can have a continuous wave laser output. What is the advantage? Advantage is that whenever I need a continuous source of light, I can use it as such. If I need a pulsed output, then I can bring in some other technique to make it pulsed. Okay. I can store the light and keep storing, and whenever I want, I open the gate, a huge amount of light comes out in a burst. So, thereby I get a pulse, all right. So, I can have continuous wave as well as also pulsed. Can be obtained, okay, by putting in some pulsing technology, which we will talk about after 2-3 classes. Okay. There are techniques called Q switching or cavity dumping or mode locking. So, these are certain techniques by using which we can create a pulsed output, okay, from an intrinsically continuous wave laser. All right. So, now at this point we will ask you a question, that is okay. So, which you should try to answer. So, out of this 2 level and 4 level system, so which one between a 2 level, sorry, it is 3 level and 4 level system can work better or more efficiently as laser. Okay. So, you try to answer this question, otherwise I will answer it in the following class. So, thank you very much.